What up, everybody? Welcome to another episode of Let's Ask Paul, the podcast where you get to submit questions to me using our free sponsored online portal, sponsored by Wix, over at paulabernathy.com. It's, again, we're not selling you anything over there. It is a sponsored page that basically allows us to be able to have a uniformed way for you to send code questions and other questions into us, and it gets routed the proper way to a folder, which again keeps it from getting lost in the shuffle with the hundreds and hundreds of emails I get each week. It's just an easy way to get your questions to me, and I'll answer either in an email or if selected in an upcoming podcast, much like today's. And if you're not listening to our podcast, so this is the first time you stumbled on it, remember we have over 800 plus episodes going back quite a few years. And you can listen to all of them on any of your favorite podcasting platforms: Spreaker, Spotify, Deezer, Apple Podcasts, Google Podcasts, Podbean. Gosh, there's so many ways. I listen on Spotify. It's my favorite platform to listen on. And I also listen on my Alexa devices because I just asked for Master the NEC podcast on the device, and it'll play the latest episode. But if you want to dig deep into all of our episodes, some of them actually has descriptions. Others that are just mobile ones may not have a description. You just got to listen to them at random. But the easiest way to listen is to get our free mobile app. It's free. It doesn't cost you anything. And we have a lot of free resources and tools on there for calculators and to use in the field. And it's neat to have on your phone. It's not going to take up any space on your phone because it's a PWA app. But go check it out over on our website, fasttracksystem.com, fasttracksystem.com. Go check it out. And it's free. And it works on any of your mobile devices, tablets, and if you click on the link, it even works on a desktop. So it's pretty neat. And install it on your phone, do a shortcut to your home screen, and if it asks you about notifications, absolutely select yes, because we send notifications from time to time, updates and different things that are going on. We want to keep you aware of them. Maybe something drops that we think is interesting, like a new blog or a podcast or something. We want to keep you engaged. And again, we're not going to take up any space on your phone, so go check that out. All right, today's episode was submitted, and the question is, Paul, can you explain the application and changes that took place in the 2023 NEC for permitted reductions for neutral conductors and prohibited reductions for neutral conductors, and how they would apply to me in the field? Thanks again for all you do, and appreciate listening to your podcasts on the job site and in the car from site to site. Well, thank you for listening. I'm glad you joined us and found our podcast. Again, remember, folks, you can listen to us from any of your favorite platforms. And do me a favor, we don't advertise and we don't market. You need to share with other people. Let them know about a great podcast that's available. And all they got to do is search for Master the NEC podcast on all of their popular listening platforms, and they can find us. Whatever they like to listen on, they can find us. Or better yet, tell them about the app that they can download on their phone. Again, won't take up any space. Okay, so let's look at this question here. So the first thing we want to talk about is, where do we go in the code? Now, I'm in the 2023 edition of the National Electrical Code. So that's what my response is going to be, based on. So if you've got a 2023 edition of the National Electrical Code, we're going to go to 220.61. Now, that part of it didn't change, right? That's not any real change from the previous editions of the NEC. That part didn't change, okay? So just want to, make that clear how that worked out, okay? Now, the only thing that really changes is in the 2023, you have a 220.61A, which is your basic calculation. Again, not a change. And 220.61B, which is permitted reduction. The only change in this really is giving some headings to what was B1 and B2, still the same, but now they've made it clear, rather than writing in the language what it was all about, like cooking, wall-mounted oven or whatever, it now has a kind of a heading to it. So there's a B1 and a B2, same as it was before, but now it kind of gives you a heads up. It says B1 is for household electric ranges, wall-mounted ovens, counter-mounted cooking units, and dryers, right? Very specific. And then B2 is unbalanced load in excess of 200 amps. All right, so it's just a structural change. It's not anything that's critically changed that's going to be too confusing. It's just kind of how it structurally went. And then, of course, you have 220.61c, which is the prohibited reductions. And again, so not any really change in that's substantive, that's too much, that's going to cause any confusion with anybody. So again, now the only other thing is that I believe, let's see here. Now, nothing additional that's worthy of me talking about any change when it comes to this. So the reason I bring all that up, because there is a wording change that is been changed in here that I'm going to address, but I just wanted to make sure that everybody following along realizes that whether you're following in the 2020 or the fact that I'm in the 2023, it doesn't mean you can't, what I'm going to talk about today is not germane to you. It doesn't matter which cycle you're in, okay? It's going to be germane either way, okay? All right. So let's kind of dig into this. All right, so right off the bat, let me tell you the change that is significant. Now, when we did permitted reductions, like this is where we took a neutral and we could reduce the size of the neutral. It used to say that when you permitted reduction, there was an or in there when it was considering between 220.61 B1 and B2. So B1 was the ranges and dryers and whatnot reduction. And then the B2 was the portion that was over 200 amps. Now in that, it used to be or. So it made it imply that you had to pick whether or not you're going to apply the 70% to the cooking equipment, for example, or the dryer. That if you did that, then if your neutral loads were over 200 amps overall unbalanced load, that you couldn't apply B2 as well. It's kind of like an or. You had to pick one or the other. Well, that's changed for the 2023 because you could apply both. You could have, obviously, a neutral reduction can apply to your neutral calculation for ranges and dryers, for example. But also, if your overall unbalanced neutral load based on a calculation is over 200, then you ought to be able to apply B2 as well for that unbalanced load in excess of 200 amperes, okay? And so that's what we're kind of going to look at today and how that would apply. Now, it wouldn't be right for us to not at least explain what a prohibited reduction is. So obviously, we're going to show you how to apply that 70% and where you would and where you wouldn't. But in the prohibited reduction, which is 220.61c, we're going to show you an example of where you're going to have to dissect out a certain value for let's say a nonlinear load that you're not allowed to apply the reduction to. And so people do ask, how do you dissect this out? So that's what we're going to kind of do today in some examples for you. Okay, we're going to give you two examples. First example is going to be just a normal load calc, whatever the system may be, delta. In this case, you have all linear loads, normal loads. There's nothing you have to worry about except for doing your calculation, and you come up with your maximum unbalanced load based on your calculation, okay? So let's look at it. So when we look at the rules, we're going to be focusing today on 220.61b2, all right? And this is for the unbalanced load in excess of 200 amperes. Now, if you do a load calculation and your load, whether it's a single family dwelling, multifamily dwelling, whatever it is, if your neutral loads exceed 200 amperes, then you're able to do a reduction. And it's going to tell you which systems you can do this on. Okay. And then, of course, the prohibitive reduction is going to tell you what systems you can't do this on, or what condition your situation is that you can't reduce it. Okay. So in our situation, I'm going to give you two. All right. So the first one, just a normal application. And we'll show you an example. And then I'll explain which systems you're not allowed to reduce the neutral load. Okay. All right. So the first example I'm going to give you, it's just you did a calc. You did a calculation and you came up with 400 amps of maximum unbalanced load. You just did a standard calculation because remember, 220.61 is in part 3, which is a standard method. Okay. So even if you do an optional method calculation under part 4, when you're sizing the neutrals, you're still going to be using part 3, right? So always good to think that if you're in the field, you're thinking, well, I would never calculate anything using the standard method, but you're going to, unless you just make the neutrals full size and don't want to do a calculation, then you're going to, you're going to be in part 3. So you need to learn how to use it. Okay. And anybody out there that tells you don't trust them, and that's not an educator you want to learn from. You need to learn part 3 and part 4 of calculations, right? Okay, so let's kind of look at our scenarios. So we've got a load, we did our calc, and we have 400 amps of unbalanced current. That's our neutral current. So in applying 220.61b2, and here's what the code says. It says that portion of the unbalanced load in excess of 200 amperes, so that means the first 200 amperes is at 100%, right? Because we're talking about the amount over 200 amps. Where the feeder or service is supplied from a 3-wire DC or single-phase AC system, a 4-wire 3-phase system, a 3-wire 2-phase system, or a 5-wire 2-phase system. And again, 2-phase systems, and whether it's a 3-wire or a 5-wire, are rare. I'm not going to cover those. But the key here is single phase or even a 4-wire 3-phase system, you can reduce the size of the neutral that exceeds 200 amps. Okay, so the first 200, 100%. Just take the first 200 and that's a given. Anything over that, you can reduce it to 70%. Now, where do we get that rule? At the very beginning of 220.61b, it says that the service and feeder supplying the following loads shall be permitted to have an additional demand factor of 70% applied to the amount in 220.61b1, and that's the value for like ranges, wall mount ovens, whatever. And then it says, and a portion of the amount in 220.61b2, which is the value that exceeds 200 of unbalanced load, right? Now, that change took place in the 2023 again, where it says and, whereas in the 2020 it said or. So it was almost made you feel like you had to pick one or the other. And that wasn't the intent. Both of them were applicable. So I can apply the 70% to my range for the service calc, but also at the end, I can do an additional reduction on that neutral overall if it exceeds 200 amperes. Okay. Now, most 1 and 2 families are probably not going to have 200 amps of maximum unbalanced load, right? So that's not going to be an issue anyway. Okay. But just so you know how it applies. So let's look at our example. We had 400 amps of unbalanced current. Just say it's a single phase AC. It's perfectly easiest way to approach it. And it is 200 amps. The first 200, obviously at 100%. Because we're worried about that portion that's over 200, and that was another 200, right? Because we said it was 400 overall. You take that portion that's over 200, which in our case is another 200, you multiply that by 70%, and that is going to be 140 amperes. Well, you take that 140, and you're going to add it back to the 200, which you took at 100%. And that's going to give you a total of 340 amperes. Well, that's going to be your maximum unbalanced load that you have calculated, and you have applied the demands, and now you're going to size your conductors accordingly, your grounded neutral conductor accordingly. Okay, straightforward. And that's the additional reduction that you can do. And remember, that is applicable in all situations, whether it's optional or standard. However, you're going to have to go and do the neutral calculation, right? Now, a lot of times people forget that you have 250.102C1, which is titled grounded conductor. So it can't be any smaller than what's in that table. So you need to always check the size that you calculate with the minimum size in that table. And remember that it can't be smaller than what's in that table. In our case, it's going to be larger because now we have to size the neutral for that 340 amps. So it's definitely going to be greater than whatever would be in that table. Okay. And so at the end of the day, we need 340 amperes, and we're going to size the conductors accordingly. Now, let's look at the prohibited reductions really quickly. Okay. Now, here's the prohibited. When you cannot, reduce a certain portion of that unbalanced load when it comes to the neutral, right? All right. So let's look at that prohibited reduction. So this is 220.61C, and it says there shall be no reduction of the neutral or grounded conductor capacity applied to the amount in 220.61C1 or portion of the amount in C2 from that determined by the basic calculation. So what that means is if we have a certain value that we calculated out of unbalanced current, if there's a certain portion of that that falls under the two items of prohibited reduction that we're going to talk about, then that portion cannot be reduced. Just that portion cannot be reduced. Okay. So let's look and see overall when we can't apply a reduction. All right. So the first one we'll look at, it says number one. So C1 says any portion of a 3-wire circuit consisting of 2 ungrounded conductors and the neutral conductor of a 4-wire 3-phase Y-connected system. So if I'm having a 4-wire 3-phase Y-connected system and I'm going to derive from it, make connections to it, and I'm going to be deriving a 3-wire circuit from a 4-wire circuit, and it's a 3-phase Y system that we're starting out with, and I'm connecting onto it to create a 3-wire circuit that's going to have, again, 2 hots and a neutral, then I am not allowed to apply a reduction to the neutral calculation that is going to be whatever is being supplied by that 3-wire circuit that's deriving from that 4-wire 3-phase Y circuit. You get me? You're just not going to have to be able to do the reduce. So whatever that might be feeding, let's say it's feeding a panel, and it's, again, for lack of a better example, tapping it off or connecting or bugging onto a 4-wire 3-phase Y in order to get that 3-wire 2 hots and a neutral, then you're not going to be able to reduce the neutral that's being supplied from that. Okay, so that's the first one. No reduction allowed. So that neutral that's running with those 3 wires, that 2 wires in that neutral that's being fed from that 4-wire 3-phase Y, wherever that's going, there is going to be no reduction on that neutral when we do that calculation for whatever that supplies, panel or whatever it may be supplying. Okay, so no reduction on that portion. Now, when it comes to C2, it says that portion consisting of nonlinear loads supplied from a 4-wire Y-connected 3-phase system. Okay, so let's do an example where we have some nonlinear current. We have a 4-wire Y-connected 3-phase system, and we have a total neutral load, folks, of 690 amps on this example. 690 amps, okay? And that's the total, that is our unbalanced current. We did the calc, that is what it is. But of that value, 250 amps of that 690 actually is considered nonlinear current. Okay, well, now we have a problem. But we can only not apply the reduction to that portion that has the nonlinear loads. For the rest of this is obviously linear loads. Okay, normal lamping, normal lighting systems, normal motor, normal loads, they're not considered nonlinear. Now, what are nonlinear loads, by the way? These are things that really are going to distort the normal sinusoidal waveform. It kind of causes disruption. You don't get neutral cancellation very easily. Things like computers, variable frequency drives, switching devices, printers, copy machines, big office buildings with a lot of electronic ballast, all those type of things will chop the crap out of a normal waveform. And it's hard for neutral cancellation when the waveform gets chopped like that. It's not a nice flow like you might look into the oscilloscope, and it looks like a normal, nice waveform. It chops it up. And it's hard to, if you think about when we talk about neutral loads, if I have a multi-wire branch circuit and I'm putting it in a panel and I'm sharing a neutral, for example, right? We just say single phase just for simplicity's sake. If I have 10 amps on leg 1 and 10 amps on leg 2, because of the cancellation effect, the neutral will see 0. If I have 10 on one and 8 on the other, the neutral will see the imbalance, which is 2 amps. Okay, this is what the neutral will see. Now, what happens in a situation where you have a lot of harmonics or you have nonlinear loads, that is not a nice cancellation effect process. It doesn't take place as nice and smooth as what we just said. So the neutral current could be as much as or equal to any of the phase conductors, depending on the system. So it can be problematic, and this is why you might see 4-wire, 3-phase systems with these nonlinear loads. You might see situations where you see white conductors that are turning brown or whatnot, and they weren't sized properly. Okay, just as an example. All right, so what we've got is we did a calculation, 690 amps, and 250 amps of that we know is nonlinear current. All right, so how do we apply the rules here? It probably just as straightforward as you can imagine. The first 200 amps is at 100%, and then you have the nonlinear current, which you have to take out because we can't apply the reduction to that amount. So that's at 100%. So you have the 200 amps that we have to take at 100, that we can't apply reduction to, right? And then we have the nonlinear current that we can't apply the reduction to because of 220.61C2, okay? That portion that is nonlinear, so I take that out, no reduction there. And so you take that 690 and you take away 200 and you take away 250, that leaves me 240 amps. That's the portion that we can apply, okay, the reduction to under 220.61B2. So we just take that 240, we multiply that by 70%, that's 168 amps. But then we apply that back to that first 200 that we have to take at 100%. And of course, we got to apply it to that nonlinear load, which we can't take a reduction for, right? We already saw that. C2 tells us we can't. So we add that back. So it's 200 plus 250 plus our 168 that we did apply the 70% to. That means the total demand that we've calculated out is 618 amps of neutral load. Now, 618 amps is a reduction from 690. And you know what? It could be a conductor size change. But this is how it applies. And that's how you're going to apply 220.61B2 for the excess of 200 that exceeds 200 amps, and how you're going to apply the prohibited reductions. Okay, and those were two examples that pretty much show you how you would do that. Hopefully that kind of makes sense, right, to everybody out there. All right. So if I ask you a question, and I'll create a scenario for you that allows us to apply what we've just learned. Okay, so the very first one, let's look at a question. So straightforward, I'm only going to tell you the question, and you're going to have to assume that none of the prohibitive reductions apply because I didn't state that they do, but I will give you an example when it does. So this is a question is, what is the neutral demand if the unbalanced current of a neutral is 566 amps? So we'll assume it's a single phase because nobody said otherwise. Or we'll assume it's maybe a 3-phase system, 4-wire, that didn't have nonlinear loads, right? So obviously we can apply the reduction here. So let's look at it. So 566 amps is the unbalanced load that we're given based on our calculations. Standard method, we calculated it out. So the rule here in 220.61b2 allows me to apply the 70% to that portion that exceeds 200 amps. So that 566, we're going to take 200 away, which is going to be at 100% because we're going to add that back at the end. And that gives me 366 amps. That is the portion that is over 200. That's the portion that we're going to apply the 70% to. So I'm going to multiply that by 0.70. And that is 256.2 amperes, right? Now I get to drop the 0.2 because, as it says in 220.5, okay, that portion, we get to drop it. And if you want to keep it, it's not going to make a difference in your equation, right? But again, you can do it at the end or you can do it here. You can even keep it. That 0.2 is not going to play a role anywhere. So in our case, we're going to take that 256.2 if you would like and add that back to the original 200. And that equals 456.2. I'm going to drop the 0.2 and it's going to be 456. And I'm going to size my conductor accordingly, right? So this is sizing the neutral for the service. Keep this in mind that if you're doing a branch circuit and you get a question on the exam that wants to know what the actual contribution is for the neutral, then all you're going to answer that is by giving the exact value, not rounding it, just the exact value. Here we're talking about a service calculation, so we're going to be rounding and those type of things again. But just keep that in mind. If you want to use the total value, that's fine. But in this case, since it was less than 0.5, then we dropped it off. So that was 456. So size your neutral conductor accordingly. Again, can't be smaller than what's given in 25102C1, but in this case, it's obviously going to be larger. So we're okay there. Now, what if I ask you this question? We'll use the same amp values, but now I tell you that 200 amps of that 200 amps of that 566 is nonlinear loads. Now remember, prohibited in 220.61c says that portion of the neutral that is nonlinear, you cannot apply the 70% to it. Okay, so that tells us that we just got to exclude that from the equation. So let's do it. So the same values, 566 amps of what we've calculated out to be our neutral loads. And so I'm going to take that 566, I'm going to subtract away 200 because we know the first 200 has to be at 100% anyway, so that's 200. So we're just going to put that aside. And so we do that, and what does that leave us? Okay, so we take the 566 minus 200. That equals 366. Now, remember what we said? 200 of that 566 is also nonlinear loads. So we're going to take away 200 from this 366 as well. So we're going to take 200 away from that. That leaves us with 166 of neutral load that we can now apply the 70% to. Remember, the first 200, 100%. Got to take the full 200. The amount over that, you can apply the 70%, but remember, we cannot apply it to those non-linear loads. So what we've got is, let's recap. We have 566 minus 200, that's the first 200, minus another 200 for those nonlinear loads that we were taking into consideration. That gave us 166. We multiply that by 70%. That gives us 116.2. You can drop the 0.2 if you choose at this point, or carry it on and go on through the math. But now I've got to add back the 200 of the original 200, and I have to add that 200 back of that nonlinear load that we couldn't reduce. So it's 116.2 plus 200 equals 516.2. I can drop the 0.2 if you would like, and that is 516 amps of now neutral load. And again, that 0.2 is the actual value. It's not going to change the value at the end of the day. Okay. So you're going to size the conductors accordingly to handle that maximum imbalance load after we've applied what we could do a reduction on and also what we could not do a reduction on. And so that's exactly how we work that entirely based on those two given examples. Okay. All right, folks, hopefully you got something out of that. Those are kind of two examples, and it kind of mixes with the whole lesson that we did today. Hopefully that answers the gentleman's question on derating the neutral, when you can, when you can't, and then how you would apply it if you have both nonlinear and you have linear loads in a calculation, what you reduce the neutral by and how you use these different rules. And it's a little clearer for you. Again, if you want to learn more about the National Electrical Code, we encourage you to check out our website, fasttracksystem.com. We have some great blogs on there that are free. Get our free mobile app from the website as well. A lot of calculators in there to make life just so much easier out in the field. We're constantly adding new things. If you want to get a great course on the National Electrical Code, check out our courses in our Fast Tracks program over on fasttracksystem.com. And if you got any questions, please, by all means, feel free to ask them at paulabernathy.com through the portal, and we'll be happy to answer any of those for you. All right, folks, till next time, stay safe, God bless, and keep learning.